Quantum entanglement is a paradox that occurs in quantum physics. However, before we get into that, we need to know a little bit more about quantum mechanics. Quantum mechanics is a new and theoretical form of physics that diverges from classical physics, where nearly everything can be measured and understood. In stark contrast, quantum mechanics is weird, abstract. It deals with things that we can barely see and detect. That's the main problem with quantum mechanics. It is incredibly difficult to attain data for use in subatomic particle physics. But that actually leads us to our golden rule. We are not allowed to assume data for use in quantum mechanics. That is, under the Copenhagen interpretation. Let me give you an example. Here we have my pal Jeffrey. If we put him in a box, Jeffrey could be any color, shape, or size, but we can't tell. From our perspective, he could be any of them, and so he is all of them at once. This is what we call a superposition of states. However, when we observe him, he is knocked out of that superposition and locks into a definite state. This concept of superpositions in quantum mechanics was developed by Erwin Schrödinger, Niels Bohr, and Werner Heisenberg as part of the Copenhagen interpretation of quantum mechanics in the late 1920s. With that in mind, time to learn about quantum entanglement. Here's the particle. It's not spinning, and we know it's about to decay into two separate particles. Whoa, look at those particles. See they're spinning? This one is spinning clockwise at a rate of 1 revolution per second. This one's spinning counterclockwise at the same rate. We'll call it 1 and negative 1. If you add those rates of acceleration, you get 0. Remember how the prime particle had no spin? But let's say we only had one particle. What happens then? Well, let's find out. So we see that the prime particle has already decayed, and we're only left with the clockwise particle. That means that the other particle has to have a counterclockwise rotation, right? Well, no. Remember, under the Copenhagen interpretation of quantum mechanics, we're not allowed to assume data for particles we haven't observed, and we obviously haven't observed the other particle. That means that as soon as we observe this particle, the other particle has to instantly conform to that, knocking itself out of the superposition and locking into a definite state. Freaky, right? Also, if we alter this particle, the other particle is also affected. It's crazy. Now, we're ready to talk about how this applies to you? Quantum entanglement can be implemented in a variety of situations, including computing and communications. Let's talk about computing. Quantum computers could revolutionize our computing systems, making them faster and smarter, allowing them to run more complex software. Companies like IBM and Google have already made vast strides in the production of these quantum computers. Quantum entanglement can also be used to have a conversation with anyone, anywhere, instantly. This type of entanglement has already been demonstrated in a lab in Brookhaven in 2019, proving that this technology isn't just theoretical, but tangible.